Kamal, let me take you through a small working example of how to do reinforcement learning. Learning is a very uh, important concept used across different use cases, specifically when you have to train an agent to uh, achieve a specific objective, right? For example, it could be like, if you have sent out offers to millions of customers and you want to say what is the most optimal offer for a given customer. That's a very classic use case where you identify the optimal use case for each customer. So, or example, another example would be, how do you identify a particular objective is met, right, with certain constraints. So I will take you through a simple example of doing reinforcement learning, nothing complicated. So let's say an agent. An agent is something which kind of is a term used to learn a particular task. So the agent has to start from here and move up to this point. If the agent moves here, he gets or she gets a reward, and if he moves here, there's a penalty. That's what we have tried to define here as a reward. Then there is something called Q table. This is called the quality table. These are the possible actions that you can take. So basically, what you need to understand is this Q table defines the set of state and actions. What is the current state and what are the different actions it can take? For example, here, the robot can move up, down, right. So your states can be from this state to this state. It can take an action up and move. So for example, it can move from here to here by taking an action of moving right. So then there is a constraint that it has to be within this boundary of 3 by 3 maze. So you define all this here. You define the Q table. Then you define the learning rate versus the discount factor. Alpha, it defines how quickly you want the agent to learn it. Even if it might learn quickly, but it might be unstable in the long term. So then the discount factor is how much weightage you want to give on to the short term rewards versus the long term rewards. Exploration rate. Exploration rate versus exploitation describes um, how what is the cost of taking a new risk versus optimize the gains from an existing state action or an existing scenario, right? So this basically, it's pretty much like, how much do you want to milk your existing situation versus what is the risk level you want to take to explore. For example, say you're taking, but you have to go to a particular, say you're trekking and you want to go to the top of a mountain. So somebody has told you that this is the map and this is what will take you easily. So that is, you're fairly sure that this is the best path, but you also want to explore, saying that hey, there might be a better path. So what is the risk factor involved in that exploration versus exploitation? That is what this epsilon will tell you. So what we have done, we have defined all the actions. We have defined a function which will help us get into the next state. So basically, we have defined a sum function from the state action map. So basically, what it does is it takes the sum of the current state and all the actions. So here's an example. Where I'll give you an example. For example, if the current state is 1 comma 1, the and the action is up, so this zip produces 1 comma 1 comma 0. So then you take the sum of all these one, 2, 3, 4 elements. You will get particular tuple. So this will be the new state, and check if this state is between the bounds, and then you either go to the next state or you stay in the current state. So what you do is you run this function. So here you define a function for the exploration versus exploitation. Then for you get a reward for each state action pair. You get the next state and the reward, and then you define the Q table by which how you maximize the rewards in the Q table. So generally, what you would have to do is you have to run this entire state action next state reward for a certain number of times, which is called an episode. For say after 1,000 episodes, you would have learned enough and you have maximized your rewards. So then you'll get a final Q training table. So this is how reinforcementing maximizes the rewards for moving for any specific objective. So if I were to take the max of all these Q, for example, so I will get the optimal channels for each of the customers. If I were to do a customer comma offer optimization problem. So this is a short example of how reinforcement learning works. Let me know if you have any.